Well, first of all, thank you for inviting me. This is a great pleasure to be in the company of these gentlemen next to me, too. They're all people I have great respect for. My name is Jim Patton. Can we advance this? Where's the button? There it is. Okay. Sorry. So I want to make a few, mention a little bit about where I come from. I now have a new lab at the University of Illinois at Chicago, but the vast majority of what I'm going to talk about today is in my other lab, which I also still work at the Rehabilitation Institute of Rehabilitation Institute of Chicago, which is located in downtown Chicago nearby. It's also been heavily affiliated with Northwestern University. And then also there's something worth mentioning here is that we are hosting as the National Center on Rehabilitation, Robotics, and actually Rehabilitation, Robotics, and Telemanipulation. And we call it MARS. MARS stands for Machines Assisting Recovery from Stroke. So my motivations very often are related to understanding control of movement, maybe in the healthy, and understanding mechanisms there. Every once in a while we study what happens to the nervous system when it breaks down, primarily in the area of stroke. More recently now my research is in traumatic brain injury as well. And then every once in a while we discover something that actually lends itself well to fostering recovery. So unlike what Dr. Shaw just talked about making robots change the way they behave, I'm going to try to talk a little bit about how robots can be used to change the way the human nervous system changes its behavior. So it's kind of a slightly different trick, but we share very, very similar ideas. Okay, so I want to, and if you can click the upper right figure, I think that's an animation as well, please. But what I want to do is briefly mention what we have at the Rehabilitation Institute of Chicago. This is not mainly my work, although I'm involved in some of these projects, but we have an awful lot of great engineering research and neuroscience research going on, focusing on how the nervous system controls movement and how you can maybe understand what's going on when it breaks down due to neurological injury and how it may be repaired using robotics. So this is a little bit different than assistive robotic technology, where you might sometimes, as in the case of this lower figure, this is Todd Kuiken's work. He works down the hall from me and has a very heavily funded project on targeted reinnervation and prosthetic limbs. So this would be a form of assistive robotics. And we also have Richard Weir, who's implanting electrodes to help control robotic devices that may be implanted or prosthetic devices that are planted on the arm. Instead, a lot of this technology is aimed at understanding how you can have an experience with a robot, a therapeutic experience, and maybe then go home at the end of the day and leave the robot having benefited from your experience. So a little bit like what therapists do, physical therapists do. And we know from a lot of the literature that repetitive practice and learning tends to be one of the key modes of recovery for almost all well-known neurological injuries. And I focused on stroke, but there's a number of people that are doing a lot of very interesting research. This is Eric Perot and his lab, where they're doing very vigorous robotic disturbances on the nervous system and studying reflexes in spinal cord injury and in stroke. Spinal cord injury is a key focus of the Locomat robot, which is now pretty well known as a robot that moves your legs for you as you walk and helps retrain the nervous system. So there's a lot of exciting research related to technology. I do technology development, but I think what's important today is to talk about the idea of software. So now it's the question of how the heck you program this robot, and maybe also how the software that sits underneath the hood of this human nervous system actually works, and how we can maybe leverage what we know about it neurologically in order to get things done. So kind of an engineering goal as we put on our neuroscientist hat. Okay, so here's kind of a motivating, here's the music. Nice Brazilian music. This is, if you can click on the left, the left one too. So these are kind of motivating examples of what I'm about to talk about. On the left, we have kind of a more primitive version of what we've been doing for years, which is having a human-machine interaction experience. And John here is playing with the robot. He's looking at a TV screen. So it's kind of a boring video game, very primitive, but interesting to play around with. And then more recently, we've gotten very fancy with our first-person immersive haptics and graphics displays. Haptics meaning rendering the sense of touch using a robot, and graphics, of course, with a stereo vision virtual reality display that's see-through. He can see his own hand, but he's interacting with objects in the environment that we render both haptically and graphically. So he can see these artificial objects and feel them because he's holding onto a robot that's rendering the touch of these objects. And there's literally no end to what we can do with these interesting ideas, and that's why we're seeing a lot of these devices out there in many labs now. The idea of robotics, of course, the central philosophy of robotics is that they're infinitely programmable and they can be made to do a lot of things. So it's a fantastic tool to have in your robotics lab because there's really no end to the experiments and the interesting things that you can try with them. So this is basically the central question that I'm going to touch on today is, can we use robotics and other feedback technology to train? And this has been something I've been working on for almost 10 years now, and we've found a lot of exciting results. I'm going to touch on some of them. I'll get rid of that silly music. One of the things that you can do is you can just use the visual graphics display technology to do interesting things. So I wanted to mention a colleague that I've been working with, Asaf Dvorkin, who's using this device simply to detect visual spatial deficits in patients. It turns out there's a very common problem in stroke survivors called hemispatial neglect, where you just simply ignore the left side of your body and things that are perceptually on the left side. And so one of the things you can do with a device like this is simply present targets in space and ask people whether they see them or not. So this is a perception task, and you can see that the patients have a very hard time reacting and determining whether there's something there at all if it's on the left side of their body, and that's really what's indicated here is the reaction time is indicated by a sphere that's proportional to how long it took the person to notice it. And then you can also just see whether they actually noticed it at all, and you can see that this patient also fails to detect anything on the left side of his body. So this is a very interesting tool there. So right away we just have a graphics tool that's interesting, and of course this is a three-dimensional system, so we can ask three-dimensional questions and be very careful about how we do it. But enough about that. I really want to talk about the combination of robotics and graphics together because I think it's very powerful. As was mentioned before, I think vision really is a critical sense, and our nervous system knows that. And our nervous system pays a lot of attention to vision as well as manual interaction with the environment. And putting them both together is a very, very powerful tool. So I probably don't need to say this, but really the interesting thing is that I think we start out with very interesting, obvious ideas of what to do with a robot to maybe make someone who's unhealthy healthier up at the top here. But really what gets very interesting is when we start using our devices and our knowledge of neuroscience together to get answers and drive very, very interesting and challenging kind of questions about either training someone to do something better using these kinds of devices or fostering recovery or speeding up recovery from a disease. So this is to keep me honest about neural control. And this has been touched on a little bit by Dr. Schall, but I want to make it clear why we have this luxury that we're going to play around with in a second. And it really has to do with the fact that our nervous system is really slow. So unlike the robots that we've seen that work at near light speed in terms of feedback technology, our nervous system, the conduction velocities of a signal from the lower parts of our body up to our brain is ridiculously slow. And because of that, we get a much more complicated control system out of this. And we rely on our expectations of the future. So when I reach for my cup of coffee, I am not using feedback control alone from my sensors to accomplish a task. In fact, very much of my reach for my cup of coffee is, of course, a plan. It's an expectation of how my arm dynamics are going to influence how I move. It's going to be an expectation of how full the cup of coffee is and how much it's going to weigh, how much my prior experience is going to have influenced this. And it's pretty obvious when you think of reaching for, say, a can of Coca-Cola and you think it's full, but it actually is empty, and when you reach for it and you grab it, your arm shoots up into the air. So there's an awful lot of very interesting things because of this extra layer of control complexity in the nervous system that we can actually use to our advantage. So this is an age-old slide, and forgive me if you all know this, but I want to take the people who haven't seen this through this really briefly. But this is kind of an interesting first experiment that's inspired a lot of recent research. And this is my colleague in the lab, Sandro Musavaldi, who has been a colleague and a mentor from way back. And he did this very interesting experiment with Reza Shadmir, who's now at Hopkins. And what they did was they basically asked people to start at a center point and reach to an outward point in many different directions over and over again. And you can see that what people do when they're reaching to these targets, which really aren't shown here, is they reach in a straight line, which is what you'd expect. I reach for my coffee in a straight line. These people are reaching in a straight line over and over again. There's a little bit of variability, but for the most part, they're straight. Their velocity starts at a nice low velocity, smoothly goes up, it reaches a maximum in the middle, and then slows down at the end. But what ends up happening is what they've done is these people are holding on to a robot as they do this, and the robot begins without resisting them at all. But now we can program this robot to do anything. We can program this robot to feel like you're bumping into a wall that's not there. You can have it feel like you're stirring soup that's very viscous. But the really interesting thing is what happens when you introduce forces that you interact with that maybe have nothing to do with anything you've ever experienced in the natural world. And so that's really what this is all of a sudden they turn on this force field, which is a vector field proportional to the velocity vector. And the important thing to remember about this is that it's just darn strange. It's not something you've ever experienced. It has a negative eigenvalue, which means that it's unstable in one direction and can really screw you up, but only in one direction. In the other direction, it's not. And the interesting thing about it is that you make horrid mistakes when you reach in the presence of this. And I think there's some noise here, yeah. So the interesting thing about it is over hundreds of movements, even while you're having a conversation with someone else or listening to music while you do this, you still recover, without being told, you recover your ability to move in a straight line. So that's very interesting. And then the most interesting thing is the idea of what happens when you turn off the forces. And I think this has been well documented in a lot of motor psychology and other psychology literature, this idea of after effects of adaptation. So now you have an expectation, and it's really very subconscious. I can do this experiment on myself over and over again and still get these kind of results, even though I'm totally aware of what's going on. But what you have is you have after effects of adaptation, and this is neat. And the reason why it's neat is because I'm an engineer, and I actually can write a model. I can create a model in a computer and actually predict this. And that's quite interesting. I think I have a slide on that. Yeah. So I'm not going to torture everybody with too many equations here, but you can actually write a general. Well, this didn't come out that well. You can write a pretty general robotics algorithm that has an expectation, has an adaptive element, and can predict the underlying motor controller, and then of course the biomechanics of the arm. And you can predict all this. And that's really interesting because what I want to do is I want to reverse engineer something here now. I want to, instead of destroy your movement capability, which is a neat thing to do and is really fun, you're all welcome to come to the lab sometime and try it. But what would be really interesting is if you could design a force field or some sort of training experience that you have for a while, and then when you turn it off, you are suddenly making a movement that is desired. So I see this as an interesting possibility for a lot of different areas, and it turns out that there's many different ways to really go about this. And so I've got kind of a list of all the goofy things I've tried over the past decade. And this is very interesting. Some of them have worked, and some of them haven't. And I think there's an awful lot of interesting, rich research still yet to be done in this area. But the basic idea is that you are manipulating the expectation part of the neural controller in the nervous system. And this could be used to help foster recovery in patients, which is really where my foundations are. But now we're turning to more interesting areas that we haven't looked at before. These areas include surgical training, where you're trying to train a surgeon to do telesurgery, or teleoperations, where you're trying to train a pilot or an operator of a remote robot to learn and do their job better. And some of these tasks, as many of us may in the room already know, are demanding mentally and difficult to learn. So I'm going to talk about a few of these now to take you through the science. But before I do, I'd like to mention kind of a schematic framework and talk about the research related to learning. So this is forgive me, the folks who are neuroscientists in the room who think this is primitive. I think it is pretty primitive idea of the nervous system in terms of motor intelligence, really. So the idea is that this is the brain on the left side, and we've learned through a lot of experiments that the nervous system does three things at least when it's making a movement. One is that it's planning the movement, another is that it's setting up impedance so that it can be robust, and then finally it's maybe trying to predict the future, which is what we see with the inverse dynamics part. So we actually are able to combine these, send these signals down, go through the spinal cord, we go through the musculoskeletal biomechanics, we interact with the environment, and we produce an output movement. And I'm not going to talk too much more about this slide, except to say that, you know, we have feedback mechanisms. They get integrated in the brain, and we have all kinds of neat red lines here. And these red lines are all the different known ways that we learn based on experience that some very bright researchers have done to quantify it. And the important point is that there really are a lot of different ways our nervous system learns and adapts to experience. There's not just one. So I would say that even though I've discovered a few, there's a lot more that needs to be done. And there's many different areas in the nervous system in which all of this stuff takes place. And so there's a lot of room for new research. Oh, and the last one is, of course, spinal cord. So I wanted to put this slide up because when I first met Stefan Schall was when this was presented back, I think it was in 2000, yes, 2000 at the Robotics and Automation Conference. And this was our first try at manipulating this kind of thing. And that was to try to see if we could make healthy people bend their movement in a pre-designed way without telling them what we were going to teach them to do. So I wanted to teach people how to move along this curved trajectory when they were moving towards a target. And the way it starts is you initially expose people to a force field, and the interesting thing about it was this specially designed force field actually bends them the opposite direction in the beginning. So this is their first exposure to it. It's bending them to the left. They train for a while, and they actually recover their ability to move near the center again in a straight line to the target. And then we turn off the forces, and we end up with this really nice conformation along the desired trajectory. The red and the blue are pretty close to each other. So this is interesting, but of course this washes out. So the critical question is whether we can do this and we can get people to stay if we want them to. These people, of course, see this as undesired in the end. They say, I want to move in a straight line, and they actually de-adapt. And so this is 60, I think it was 60 movements of de-adaptation that I'm showing here, the final phases of it. So this is an interesting phenomenon, and we can do it in healthy, but can we do it in stroke? And the answer is yes. So what this tells us is that the broken nervous system still retains its ability to adapt. But here's a great example. This patient came into the lab, and when we just had them reach to targets from a point here down to here, the healthy person would do this red dotted line. And what I'm showing is the average trajectory in dark blue of this patient who kind of had I would say a counterclockwise distortion of his movement, even though he was trying to move to the target. And the interesting thing about it is what we did with this guy was we turned on forces that actually magnified his mistake for a while. And then we turned it off, and we left it off for 60 movements. So this is long past the time that a healthy person would de-adapt. But this person got to see themselves do it better after the training, and they seem to have retained the benefit, at least to some extent here. So this was very exciting, and it's kind of led to a lot of other interesting work. So I'm going to speed through this. I'm going to say that this figure kind of illustrates how, if you look at all the subjects in the study, we got really interesting results that showed that if your training forces magnify your errors versus reduce your errors, you get a benefit. Otherwise, you don't. And in the interest of time, I'll show that we've kind of made this more sophisticated and shown that patients do recover their ability to move in a straight line if we get fancier with our programming. So, and this is actually group results from this follow-up study that we did. I'm running out of time, so I want to make sure I get to the end. I want to mention quickly this idea of error augmentation. So this is an interesting phenomenon, and I think it's very useful in many areas. I think it's useful in people recovering from neurological injury. I think it's interesting in the area of training someone to do something using a robotic technology. So what I'm going to do is talk quickly about kind of an idiot view of how to do this. You can program a system to amplify the error in many different ways, and we did an investigation on how you could do that. One way to do it is to actually multiply a person's error, and then we also looked at the possibility of doing the next possible thing, which is a shift or an offset based on the initial error E0 that the person made. So if we do that, what we ended up with was, especially for this offset condition, we ended up with a much faster learning curve. In fact, if I show, I think on the next view, so these are these different conditions, control, ×2, offset, and then we actually tried ×3, which is actually 3.1 for strange reasons that I can't get into now. But the idea is that if we change the feedback conditions so that we are actually amplifying people's error while they're training, they actually do much better. This is time constant of learning. How long does it take for them to learn? And you can see that we've really, really improved the amount of time that someone takes to learn this particular task that we've given them. So that's very exciting. We think there's some sort of sweet spot here where if you're multiplying error, you lose it after a while, though, where there's definitely conditions where this systematic approach won't work. Okay. So I think I'll skip that part and talk about our current work real briefly. This is the idea that if the therapist is actually sitting next to the patient, then the patient and the therapist can work together. The therapist could actually hold on to a tracking device and give a give a cursor to the patient, and now we have a desired location, and we have a current location of the patient's hand, and we can actually use that to amplify the error at each instant in time, and we can do a tracking test. So this is current funded research by NIDER for looking at this in a clinical design. And I think in the interest of time, I probably should stop and just put up a thank you slide. Okay. All right, but thank you.